This video goes with Lesson 14, where you'll be introducing polyatomic ions to your students. Learning these polyatomic ions can be quite the challenge for some, so hopefully this video will give you some pointers to make the job go a little easier. Let's begin by looking at an example of a polyatomic ion and making a couple of points here. First thing, the name polyatomic ion indicates that more than one element is present in that ion. So for example, let's look at nitrate. Nitrate is made up of a combination of the nitrogen atoms and oxygen atoms, and because polyatomic ions function as a unit, they work together as one ion, we always use parentheses to help remind us of that, so that this nitrogen atoms and the oxygen atoms do function together as one unit. We have parentheses, and then the charge that that ion has is always written on the outside of the parentheses. So in this case, nitrate has a -1 charge, and to make it complete here, we'll indicate that it does have 3 oxygen atoms for every 1 nitrogen atom. So nitrate, the polyatomic ion nitrate, NO3, written with parentheses, and the charge on the outside. Now later on, when we take these polyatomic ions and make them into compounds with other ions, the number of each component that we will use will be indicated by a subscript on the outside of the parentheses. Again, that indicates we're taking this whole unit here, this whole NO3 unit, as one, and with the other cation in this case to make the compound. So what I like to do is using the master list in your book that's over here on page 129, I like to go through this list with you and point out some similarities, differences, and then some memory aids to help you and your students get a good grasp on these ions. The chart is divided into two halves. Here we've got the anions on this side, which tend to be a little more difficult to understand or to memorize, and then we have the cations over here on this side. Let's start with the anion set, and we'll just work our way down through those. Now, there's a couple of things that we need to point out with the anions, and that is, if the name of the anion ends in ITE, or the name the ending is ATE, those are indicators that tell us that oxygen will be present somewhere in that anion. So if it ends in "ite" or it ends in "ate", oxygen is present. Example of that, like we just looked at, was nitrite, and then nitrate is the one we just looked at. Nitrite is made up of nitrogen and oxygen atoms, and nitrate is made up also of nitrogen and oxygen atoms, and it's the number of oxygen atoms that varies, which determines if its name is nitrite or nitrate, and we'll look at that here in just a moment. So if it ends in "ite" or "ate", that means oxygen is present. Another example of that would be like our chlorite and chlorate, perchlorate. They all end in "ite" or "ate", and you'll see that they've got oxygen present in their formula. We've got sulfite and sulfate, mixture of sulfur and oxygen, and the sulfate, another mixture of sulfur and oxygen. With the nitrite, nitrate, we've already discussed. Chromate is CrO4, oxygen is present. Permanganate ends in ATE, again we've got oxygen present. Phosphate, PO4, phosphate, 8 ending, and we've got oxygen present there. So if it ends in "ite" or "ate", always know that oxygen will be present somewhere in that compound. Now, there's another rule that goes along with this "ite" or "ate" ending, and that is of the pair, like in the case of nitrite and nitrate, the ion that ends in ITE will always have fewer oxygens than the ion that ends in the ATE. Okay, I'll say that again. The ion whose name ending ends in ITE has fewer oxygens than the anion whose ending is ATE. So if we look at our example of nitrite and nitrate again, the nitrite is going to have fewer oxygens. So nitrite is going to be NO2 and nitrate NO3. Ite is less than 8. NO2, NO3, and in this case they both have a minus 1 charge. Okay, so ite's always less than 8. If we look at another set is sulfite and sulfate. Sulfite is SO3, and we'll put our parentheses. It's got a -2 charge. Sulfate is going to have more oxygens. It's SO4, and again a -2 charge. So the ending ite, sulfite, has fewer oxygens than the 8 ending sulfate, which would have the 4 oxygens here. So ite's less than 8. Okay, now let's go to our list now and begin working down through it. The first one on the list there's acetate, and I'm going to skip that one to begin with. Some of these anions on the list are ones that your students will already be aware of, the monoatomic ones, and those are the ones that we could determine charge by their location on the periodic table. An example is bromide here is a halogen, and so it's going to be Br -1. Now the next one down is carbonate. And we see the ATE ending on that one, and so we know it's going to have oxygen. So we have carbon and oxygen. Okay, and in this case the symbol for carbonate is CO3. We'll have our parentheses, and it's a -2 charge. Now understanding, being able to somehow calculate these charges on these polyatomic ions can be really tricky, and sometimes they just don't make sense what their charge is. So I just tell my students we'll just have to learn them, memorize if necessary, and go with that, because being able to figure out why it's a -2 charge is just hard to do. So carbonate be CO3 -2. Now these little memory aids that I'll introduce you to are some silly little sayings that we've made up over time that tend to help a student remember the symbol and charge. Carbonate is an anion that's used in carbonated water, which gives the fizz or bubble in pop. And so the memory aid for carbonate is Coke, which is pop. Coke at 3, you'll be up till 2, like the caffeine in the pop. So carbonate is Coke, kind of the CO here. Coke at 3 in the afternoon will keep you up till 2 in the morning. Coke at 3 up till 2. So you can use that memory aid if you like. If not, you can make your own, or just have your students work on memorizing that one. Okay, so that's carbonate. Now the next set we have are a set here that are shaded in gray, and they all have chlorine in them. The first one is chloride. Note that it's an IDE ending, IDE, so there's that to indicate that we don't necessarily have oxygen present in that one. So chloride, if you recall, is just a halogen, so it's just going to be the Cl -1. Now the next 4 I want to focus on here. The first we have is hypochlorite, then we have chlorite, chlorate, and perchlorate. Now note that of all those 4 there, they all end in ite or ate, which it tells us that there is a varying degree number of oxygen present in those 4. So the first we had was hypochlorite. So we're gonna go ahead and do our ClO. They all have chlorine and oxygen. Oops, hang on, let's start again here. Make this better. Yeah, they all have chlorine and oxygen. It's a little tricky taping this and writing at the same time here. Chlorine and oxygen. All right. So we have hypochlorite, chlorite, chlorate, and perchlorate. and it's the number of oxygens here that varies as we go from one anion to the next. Okay, the first is hypo. The prefix hypo, the HYPO here, hypo means low or reduced, like in hypothermia, it's a very cold condition, or a hypodermic needle goes underneath the skin. So hypo means low, which means that hypochlorite has the lowest number of oxygens, which is 1. Okay, so hypochlorite, then we just have chlorite, which is the next one on the list, will have 2 oxygens. Then we have chlorate, it's going to have 3 oxygens. And the fourth one on the list, if we go back here and look, is perchlorate. And the per prefix here is short for hyper. And something that's hyper, like hyperthermic or hyperactive, has excess or more or beyond. So hyper, and they shorten it to just the per part here. So perchlorate is going to be the one that has the most oxygen. In this case, it's got 4. So we have hypochlorite, then we have chlorite, chlorate, and perchlorate. 1, 2, 3, 4. We'll put our parentheses again to show that they all function as units. And for this one, they all have -1 charge. So again, memorizing the charge is probably the best approach to take, because to understand how they can all have a -1 and all this varying number of oxygens is difficult to explain. So here's our chlorine set. Remember that chloride was the first one, ended in IDE, no oxygen, Cl -1. Okay, let's go back to our chart now. Let me get these off the board best we can. Alright, going farther on down the list, we've got fluoride, again halogen, iodide, oxide, all can be found on the table, and you can, they're monoatomic ones, get their charges. Sulfide next, then we have sulfite and sulfate. Sulfite and sulfate end in ITE and ATE. Sulfite is SO3. Sulfate, SO4. Remember the ite less than the 8. Okay, so we have sulfite, sulfate. These both carry a -2 charge. Alright, the memory aid we have for this set is we get out of school between 3 and 4 in the afternoon, but sometimes at 2. So, sulfite, sulfate, we've got the S for the word school in that memory aid. We get out of school between 3 and 4, but sometimes at 2. So, there's your memory aid for sulfite and sulfate. Now the other one just above that on the chart was sulfide, ends in IDE, IDE, so no oxygen, just S -2. And what you might note here is, look, we got a -2, we got a -2, -2. It's easy to recall the charge here on the sulfide because you can just find it on your periodic table and note that it gains its electrons to get that -2 charge. And then if you recall, if you see, we've got sulfur, 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 -2, -2, -2. So if that helps you anyway in getting a handle on the charge for the sulfite and sulfate, go ahead and use that. Okay, back to our table here now. The next two we've got are nitrite, nitrate, ending in ite. So we know we've got oxygen, we've got nitrite, nitrate. Okay, ite's less than 8, so that's going to have the 2. Alright, and we'll put our parentheses to show they function as units. Ite's less than 8, NO2, NO3. In this case, charges -1s. Now, don't ask me why. Just another memory type situation, memorizing situation. So we have nitrite, nitrate, both -1 charge. Memory aid that I share with my students on this one is that it's dark, or it's night, between 2 and 3 in the morning, but darkest at 1. Okay, so it's night between 2 and 3 in the morning, but darkest at 1. So NO2 minus 1. And keep in mind, we're still going down this list of anions, and so our charges are always going to be negative charges here. Alright, so it's nitrite, nitrate. Alright, back to our list. Getting closer to the bottom here. The next two are some really strange ones. We've got chromate and dichromate. Endings 8, ATE, so we know we've got oxygen. Chromate, the other element is going to be the chromium and the oxygen. Chromate is CrO4, minus 2. And then dichromate, the di tells us we're going to have 2 of the chromium atoms, so it's Cr2O7, which is really a strange one here. And we got our parentheses, but thank goodness only also minus 2 charge. So if you can remember the charge for chromate, you can get the dichromate charge there as well. So a memory aid for this one is I tell my students that chromate and sulfate are relatives. In other words, they've got some similarities. If you go back to your chart and find sulfate there, sulfate was SO4 minus 2, and so you can see they both have 4 oxygens, they both have minus 2 charge. So we tell students sulfate and chromate are relatives and have those similarities. Alright, and you may be able to come up with another memory aid for these two here on your own, or your students can come up with some. Okay, so we go back to our list. We've gotten down to cyanide. Cyanide is a mixture of carbon and nitrogen. Just takes 1 of each and a minus 1 charge. Cyanide is a poison, often used to kill rodents and other unwanted creatures, and so sometimes we say too much CNN is poisonous, like too much television. CNN television is poisonous, so cyanide, CN minus 1 for cyanide there. Next is permanganate. Permanganate, it ends in ATE, tells us we've got oxygen. Manganese is the other element present. Permanganese, if you recall back when we did the perchlorate, which was the hyper one that had the 4 oxygen, permanganate's the same way. It's got lots of oxygen, high oxygen. So permanganate is MnO4. We've got parentheses and minus 1 charge. So permanganate, MnO4 minus 1. Okay, back on our chart, we're down to peroxide. Peroxide, again, per means excess, high. In this case, peroxide doesn't have 4 extra oxygen. It's only going to have 2. If we think about oxide, oxide is O minus 2. Peroxide is going to be O2 parentheses minus 2. So hydrogen peroxide is a common example of the use of the peroxide anion here. So peroxide is O2 minus 2. So it's just extra higher amount of oxygen in the anion here for you. Okay, so peroxide. Phosphate is the next one. Note that it ends in ATE, so it's got oxygen present. Phosphorus is the other element. Get our parentheses. Now phosphorus is the and phosphates are compounds found on the heads of matches. Okay, get these matches out here. The red and the white on the head of a match are phosphorus compounds, and so phosphate, the memory aid, we say, well, it takes 3 matches to make a fire. With the matches here, 3 matches to make a fire, and Oh, hang on. We're gonna try this one again. Told you wrong here. It takes 4 matches to make a fire. 4 matches make a fire, but 3 will work. Okay, so phosphate, PO4 minus 3. And you may note with your students that phosphate is the only minus 3 anion that we'll have on our list. The other ones are all minus 1s, minus 2s. Phosphate's the only minus 3. So PO4, 4 matches make a fire, but 3 will sure work. PO4 minus 3. Okay, that's our phosphate. We're almost to the bottom here. The last one is hydroxide. Hydroxide. Now, this one doesn't quite follow those nice itinate rules and ide rules that we had earlier. Hydroxide is OH minus 1. So OH minus 1 is hydroxide. The memory aid for this one refers to at one time there were a set of cookies that you could buy at the store that were called Hydrox cookies, and they were kind of a generic form of Oreo cookies. And so the memory aid here is, oh, it's a Hydrox cookie. So we've got oh, like oh boy, it's a Hydrox for the hydroxide cookie, and you can never only eat one. So oh, it's a Hydrox cookie that you can never eat one of. So OH minus 1 is the hydroxide. Okay, the one we skipped at the very top of the list was acetate. If we go back up to the top of your list, acetate is truly a polyatomic ion because it has 3 elements present in it. It's got some carbon, it's got some hydrogen and oxygen in it. In the case of acetate, it's C2H3O2. Makes acetate, and we'll put all of it, wrap it up in parentheses. Has a minus 1 charge. Acetate is the anion. If we were to go ahead and link it with a hydrogen cation out here, this is acetic acid. And acetic acid is a fancier term for vinegar. Acetic acid is vinegar, and I'm going to go ahead and take that off so we're not getting confused here. If we look at the acetate ion itself, it's part of acetic acid, which is used to make pickles. And so my students came up with this memory aid. They said in 1 jar of pickles, so we have a minus 1 charge, in 1 jar of pickles you can find 2 curvy pickles, 3 straight pickles, and 2 pickles that are circular, 2 circle pickles. So in 1 jar of pickles you can find 2 curvy pickles, 3 straight pickles, and 2 circle pickles. So C2H3O2 is acetate, which makes up acetic acid, which is vinegar, which is used to create pickles. Okay, so that ends our list here of the anions that we're going to use from this point forward in the friendly chemistry text. We'll look next at the cation side here. Let's look now at the cation side here. Now, there aren't very many polyatomic cations. If we scan down the list, the first one we see here is hydronium, then there's ammonium, and that's just about it. So most of these are cations that you'll have already presented to your students as monoatomic cations. There are a few here that we'll look at that are a little more odd, and we'll look at charges on those too. Now the first 2 we have here are aluminum and chromium. Aluminum and chromium, and a memory aid here is, I like to tell students, aluminum and chromium, third cousins. They're both plus 3s. Aluminum, chromium, plus 3s. They're third cousins. All right. Next on the list we have hydrogen, sodium, lithium, potassium. Recall that those are all members of the sodium family, therefore they're all plus 1s. Then we have calcium, magnesium, and strontium, all members of the calcium family, all plus 2 cations. Then we have nickel and zinc. Now those are both members of the transition elements, or those outlaws that are there in the center part of the periodic table, and so determining their charge based upon their location is tricky on the periodic table. So those two are two that you'll just need to have your students memorize. A nickel is Ni plus 2, zinc, Zn plus 2. And memory aid for this one is just kind of silly, but it tends to work. I tell my students that the N of the nickel looks like almost a 2 tipped over on its side. So if you tip that N over, kind of looks like a 2 to help them recall the charge of a plus 2. And then the Z on the zinc also almost looks like a 2, and you can get the plus 2 charge. So I say the N and the Z look like 2s in nickel and zinc for those two cations there. If we go back to our list, next is silver. Is another one that's tricky to know what its charge is based on location. Silver is Ag plus 1, and some kids say, well, the sides of the A are nice and straight and they look like 1s, and therefore we've got the plus 1 charge there for silver, Ag plus 1. Okay, moving on down, here's our first polyatomic cation. We have hydronium. Hydronium, now the name hydro refers to water, and hydronium is H3O parentheses plus 1. And so hydronium looks a lot like the compound water, which is H2O. We've added one more hydrogen atom here to make hydronium, which is H3O. And so the memory aid for this one is that hydronium is glorified water. It's water with an extra hydrogen. So H3O parentheses plus 1 outside the parenthesis here is hydronium. Glorified water, hydronium. Moving down, next we have cesium, which was a member of the sodium family, so Cs plus 1. Now we have ammonium. Ammonium is NH4 plus 1. Now ammonium is slightly different from the compound, which is ammonia, which is NH3, and that's a stable compound as written, just NH3, and then it becomes the ammonium cation if we add one more hydrogen atom. We had NH3 here, now we have H4 here to make ammonium, end in UM, and this is just ammonia, which is the compound often used as a cleaning agent or a sniffing salt. If a person is unconscious, they wave it under their nose, and that's the ammonia compound here. So this is ammonium. Memory aid for this one, these ammonia compounds are often used in fertilizer for plants. Farmers use ammonium-based compounds to get nitrogen. So what they're trying to do, get nitrogen into the plant, greener, healthier leaves for the plant, corn or whatever they're growing. And so we say farmers fertilize with ammonium, and they do it from 4 in the afternoon till 1 in the morning. So nitrogen, ammonium, NH4, farmers fertilize from 4 in the afternoon till 1 in the morning to get their crops the nitrogen that they need. Ammonium there. All right. Now, we look now, this last set of cations here all have a Roman numeral in their name. We've got mercury 1, mercury Roman numeral 2, copper 1, copper 2, tin 2, tin 4. Then we have lead and iron. Lead is lead plus 2 and plus 4, and iron is iron 2 and iron 3. The Roman numeral here tells the charge that the cation is utilizing at that time under those conditions. So mercury 1, if it's mercury with the Roman numeral 1, it's just Hg plus 1. Mercury 2, Roman numeral 2, is Hg plus 2. So the Roman numeral tells the charge. So these, in a sense, are really easy to know. The Roman numeral tells the charge. So we have copper 1, copper 2. Copper 1 is just going to be Cu plus 1, and copper 2, Cu plus 2. Okay, 10(2) and 10(4). 10, I say 10 is SN, SN. 10(2) is 10 plus 2. 10(4) is SN plus 4. Lead, plumbers use lead, so there's for its PB. Plumbers, plumbum is the old name for lead, so it's lead 2, PB plus 2. Lead 4, PB plus 4. And then the last two we have iron. Iron, if you recall, is Fe. Iron 2 be Fe plus 2, and iron 3 is Fe plus 3. Now, this Roman numeral system of naming these cations came as a result of confusion in an older naming system. They used to use endings of IC and then OUS, ick and us, as ways to indicate the different charges or oxidation states for these cations. For example, copper, there used to be the cation cupric. I got an extra I in there now. Cupric, and there was cuprous. And there was confusion when people to remember, well, which one's the plus 2 or the plus 1, and which is the plus 2, when they would just look at compounds on the shelf. We've got this cupric nitrate, then we've got this cuprous nitrate, and I know I need the one that's the plus 1, but I can't remember. So to eliminate confusion in labeling, chemists have gone to this Roman numeral system, so we just have copper 1, copper 2, and the 1 and 2 tell right away what the charge is for that particular cation. So those with Roman numerals tells the charge there for you. So that's our list of cations now. On our list, we've looked at the anions. We just need to recall that if it ends in ite or ate, oxygen's present. Ite's less than 8. Then we've got some hypos and some pers in there. Hypo is low, per is high. Just keep in mind to use parentheses when you have polyatomic cations, and keep the charge on the outside of the parenthesis, and emphasize that that charge has its effect over everything within the parentheses. The ion acts as a unit. You don't separate parts out of that. And then the next lesson, lesson 15, we'll begin making compounds using these. We'll link cations with the anions and make compounds. And again, we'll follow those same rules, putting the subscript outside the parenthesis. Well, I hope this video helps make a little more sense out of this crazy list of polyatomic cations that we're going to use in the course.